In Part 2 of Lecture 3, we will discuss process creation and termination. The operating system's principal responsibility is controlling the execution of processes. This includes determining the interleaving pattern for execution and allocating resources to processes. The first step in designing an operating system to control processes is to describe the behavior that we would like the processes to exhibit. We can construct the simplest possible model by observing that at any time, a process is either being executed by a processor or not. In this model, a process may be in one of two states, running or not running, as shown in the figure. When the operating system creates a new process, it creates a process control block for the process and enters that process into the system in the not running state. The process exists, is known to the operating system, and is waiting for an opportunity to execute. From time to time, the currently running process will be interrupted, and the dispatcher portion of the operating system will select some other process to run. The former process moves from the running state to the non-running state, and one of the other processes moves to the running state. From this simple model, we can already begin to appreciate some of the design elements of the operating system. Each process must be represented in some way so that the operating system can keep track of it. That is, there must be some information relating to each process, including current state and location in memory. This is the process control block. Processes that are not running must be kept in some sort of a queue, waiting their turn to execute. The figure here suggests a structure. There is a single queue in which each entry is a pointer to the process control block of a particular process. Alternatively, the queue may consist of a linked list of data blocks, in which each block represents one process. We will explore this latter implementation subsequently. We can describe the behavior of the dispatcher in terms of this queuing diagram. A process that is interrupted is transferred to the queue of waiting processes. Alternatively, if the process has completed or aborted, it is discarded or exits the system. In either case, the dispatcher takes another processor from the queue to execute. When a new process is to be added to those currently being managed, the operating system builds the data structures that are used to manage the process and allocates address space in main memory to the process. We describe these data structures a little later in the lecture. These actions constitute the creation of a new process. 4 common events lead to the creation of a process, as shown in the table you see here. In a batch environment, a process is created in response to the submission of a job. In an interactive environment, a process is created when a new user attempts to log on. In both cases, the operating system is responsible for the creation of the new process. An operating system may also create a process on behalf of an application. For example, if a user requests that a file be printed, the operating system can create a process that will manage the printing. The requesting process can thus proceed independently of the time required to complete the printing task. Traditionally, the operating system created all processes in a way that was transparent to the user or application program, and this is still commonly found with many contemporary operating systems. However, it can be useful to allow one process to cause the creation of another. For example, an application process may generate another process to receive data that the application is generating and to organize those data into a form suitable for later analysis. The new process runs in parallel to the original process and is activated from time to time when new data are available. This arrangement can be very useful in structuring the application. As another example, a server process, for example a print server or a file server, may generate a new process for each request that it handles. When the operating system creates a process at the explicit request of another process, the action is referred to as process spawning. When one process spawns another, the former is referred to as the parent process, and the spawned process is referred to as the child process. Typically, the related processes need to communicate and cooperate with each other. Achieving this cooperation is a difficult task for the programmer. This topic will be discussed in Lecture 5. A computer system must provide a means for a process to indicate its completion. A batch job should include a halt instruction or an explicit operating system service call for termination. In the former case, the halt instruction will generate an interrupt to alert the operating system that the process has completed. For an interactive application, the action of the user will indicate when the process is completed. For example, in a time-sharing system, the process for a particular user is to be terminated when the user logs off or turns off his or her terminal. On a personal computer or workstation, a user may quit an application, for example, word processing or spreadsheet. All of these actions ultimately result in a service request to the operating system to terminate the requesting process. Additionally, a number of error and fault conditions can lead to the termination of a process. The table on the slide lists some of the more commonly recognized conditions. Finally, in some operating systems, a process may be terminated by the process that created it, or when the parent process is itself terminated. If all processes were always ready to execute, then the queuing discipline suggested by the earlier slide showing the two-state process model would be effective. The queue is a first-in, first-out list, and the processor operates in round-robin fashion on the available processes. That is, each process in the queue is given a certain amount of time in turn to execute and then return to the queue unless it's blocked. However, even with the simple example that we have described, this implementation is not enough. Some processes in the not running state are ready to execute, while others are blocked, waiting for an input-output operation to complete. Thus, using a single queue, the dispatcher could not just select the process at the oldest end of the queue. Rather, the dispatcher would have to scan the list looking for the process that is not blocked and that has been in the queue the longest. A more natural way to handle this situation is to split the non-running state into two states, ready and blocked. This is what you see on the slide. The 5 states in this new diagram are running, the process that is currently being executed. For this lecture, we will assume a computer with a single processor, so at most one process at a time can be in this state. Ready, a process that is prepared to execute when given the opportunity. Blocked or waiting, a process that cannot execute until some event occurs, such as the completion of an input-output operation. New, a process that has just been created but has not yet been admitted to the pool of executable processes by the operating system. Typically, a new process has not yet been loaded into main memory, although its process control block has been created. Exit, a process that has been released from the pool of executable processes by the operating system, either because it halted or because it aborted for some reason. This figure indicates the types of events that lead each state transition for a process. The possible transitions are as follows. Null. New. A new process is created to execute a program. This event occurs for any of the reasons shown earlier. New to ready. The process will move the operating system will move a process from the new state to the ready state when it is prepared to take on an additional process. Most systems set some limit based on the number of existing processes or the amount of virtual memory committed to existing processes. This limit assures that there are not so many active processes as to degrade performance. Ready, running. When it is time to select a process to run, the operating system chooses one of the processes in the ready state. This is the job of the scheduler or dispatcher. Scheduling is explored later. Running to exit. The currently running process is terminated by the operating system if the process indicates that it has completed or if it's aborted. Running ready. The most common reason for this transition is that the running process has reached the maximum allowable time for uninterrupted execution. Virtually all multi-programming operating systems impose this type of time discipline. There are several other alternative causes for this transition, which are not implemented in all operating systems. Of particular importance is the case in which the operating system assigns different levels of priority to different processes. Running to blocked. A process is put in the blocked state if it requests something for which it must wait. The request to the operating system is usually in the form of a system service call. That is a call from the running program to a procedure that is part of the operating system code. For example, a process may request a service from the operating system that the operating system is not prepared to perform immediately. It can request a resource, such as a file or a shared section of virtual memory, that is not immediately available. Or the process may initiate an action, such as an input-output operation, that must be completed before the process can continue. When processes communicate with each other, a process may be blocked when it is waiting for another process to provide data or waiting for a message from another process. Blocked to ready. A process in the blocked state is moved to the ready state when the event for which it has been waiting occurs. Ready to exit. For clarity, this transition is not shown on the state diagram. In some systems, a parent may terminate a child's process at any time. Also, if a parent terminates, all child processes associated with that parent may be terminated. Block to exit. The comments under the preceding item apply here too. Let's return to our simple example. The figure on this slide will show the transitions that our three processes will have, assuming now that we have the three states of ready, running, and blocked. The figure on this slide suggests the way in which a queuing discipline might be implemented with two queues, a ready queue and a blocked queue. As each process is admitted to the system, it is placed in the ready queue. When it is time for the operating system to choose another process to run, it selects one from the ready queue. In the absence of any priority scheme, this can be a simple first in, first out queue. When a running process is removed from execution, it is either terminated or placed in the ready or blocked queue, depending on the circumstances. Finally, when an event occurs, any process in the blocked queue that has been waiting on that event only is moved to the ready queue. This latter arrangement means that when an event occurs, the operating system must scan the entire blocked queue, searching for those processes waiting on that event. In a large operating system, there could be hundreds or even thousands of processes in that queue. Therefore, it would be more efficient to have a number of queues, one for each event. Then, when the event occurs, the entire list of processes in the appropriate queue can be moved to the ready state. One final refinement. If the dispatching of processes is dictated by a priority scheme, then it would be convenient to have a number of ready queues, one for each priority level. The operating system could then readily determine which is the highest priority ready process that has been waiting the longest.